طيب خلينا نبدأ. بسم الله الرحمن الرحيم. What we need to talk about today is about the inductance. This is a very simple course. I actually didn't change this lecture as the capacitor and the resistor. And so it's going to be really simple. Inductances are really complex components. They are really, they have some nonlinearities that are really too complex to address in a very simple course like this. So basically you can take a whole course about the how you treat the ferromagnetics and the transformer, how to design the transformer, and how to do things of that sort. But now we're just going to take the basics because actually we don't have much time, first of all, and basically none of you will most likely be working with inductances except for a few. Probably if you have very specialized applications, you might need to work with ferromagnetics, things of that sort. These are more toward the power, electrical power program, not the communications or the computer or biomedical applications. So basically, first of all, let me give you some announcements. First of all, regarding the lab, okay, you have now experiments 6 and 7, okay, are basically now you should simulate them and submit the report. Just a simulation. From what I understood from Engineer Mutahir is that you usually do the simulation for all the experiments. And basically, after you do the simulation, you do the actual experiment. Here, all you have to do is just a simulation. So basically now you're going to find an assignment or an assessment tool where you just submit the report of the simulations of experiments 6 and 7. That's it. Okay, so please do that. If you have any questions, please ask the engineer. You can send him an email or communicate with him with WhatsApp. Any means of communication that you prefer with the engineer, just go ahead and do that if you have any questions, okay? And basically, if you just do the simulation, you're just gonna get the full mark. You're not gonna, basically, if you do a simulation that is correct, you're just gonna get the full mark from each one of these experiments, okay? This is, first of all, this is the lab experiment 6 and 7. For experiments 1 through 5 that you already did, please submit reports. Please submit the reports. Okay? The deadline is March 29th. March 29th, basically you should already have these experiments. From what I understood also from the engineer is that he has the hard copies of your reports, but they are all in his office. He cannot access them. So what's going to happen now is that I'm going to send him the report that you're going to submit on Blackboard, and he will grade them again. And basically, I will post the grades once he does that. Okay, so it's very important. It's very important for you to do that. Okay, if you don't do that, basically he's not going to be able to post a grade for you. Okay, so in order for you to get your grade, please submit experiments 1 through 5, and please submit them in a timely manner. Submit them by March 29th. Okay, March 29th is basically on Sunday, so please submit them this weekend. You should already have them, and basically for both experiments, for both of these actually, please only one member can submit. Okay, this is the same, by the way, for the project. Okay, one member just submit the report, and that's it. It will be counted for all of you, for all the group. Okay, so based on the names of each report, we're gonna post the grades on Blackboard. Okay, so please go ahead and do that. Okay, so first of all, the lab is done now. The second thing, once we finish these experiments, we're going to schedule the lab exam. It's going to be a simple exam on Blackboard. I expect it to be like maybe 15, 20, maximum 30 minutes of MCQ questions, or very, very simple questions on Blackboard, and that's it. This will be it for the lab, basically. Regarding the report, the project, I received only 2 teams, the names of 2 teams, okay? I need the rest, okay? Please submit your team to me by email or by WhatsApp or whatever, okay? I need to have everybody in teams as soon as possible. I assume that if you don't have a team, then you haven't started yet on the project. You cannot finish the project in one night. If you're planning to basically before the deadline to get started on the project, you're not going to do a good job in the project in this case. Okay, you have to have your team and basically distribute the tasks over the team members so that you can actually finish and do well in your project. Okay, so please send me your teams by Sunday if possible. Okay.
Doctor?
Yes.
For the lab exam, what should we study?
I'll let you know exactly, but basically it's a kind of question that you would expect to have in the oral exam, basically. It's going to be about the experiments themselves. It's going to be about the how you computed several things, like how you computed the error, for example, in the loading error, how you computed the loading error in the experiment, things of that sort. It's going to be based on the actual experiment that you did already.
Okay, thank you.
Okay?
Yes, okay.
Any other questions? Okay. So let's go back and look at the lecture, okay? So as I told you before, we're going to just cover the basics here. We're not going to get into much of the details about the inductance, especially when you have a ferrite core inductance. Ferrite core inductance are highly nonlinear, meaning that their behavior will change with the current. So imagine that you have a component, whenever you have a different current passing through the same component, it will behave differently. So we don't have much time to deal with things of that sort, and they are not easy to deal with to begin with. They are really difficult to deal with. So basically, when I consider the idealistic inductance with a few simple modifications, a few simple additions, okay? So basically, the inductance is any circuit in which a change in current is accompanied by a change of flux. Meaning that basically we're going to talk about if you pass a current through an inductance, there will be a change of magnetic flux within the coil itself, okay? And basically if you have a change of current, you're going to induce EMF that is said to be inductive or basically self-inductance or milli-inductance in that coil, okay? The unit of inductance is Henry, as we know. And basically, the relationship between the voltage and the current in the inductance is basically considering the voltage here as E as electromotive force, but actually you can just call it V. So V is L times di by dt. If you remember, for the capacitance we have I was equal to C dV by dt. Okay. Now we have for the inductance we have the opposite. We have the voltage as L di by dt. Okay. So basically, if we have an example, if we have a current passing through a coil having an inductance of 0.5 Henry, basically it went from 5 amperes to 2 amperes in 0.05 seconds. Let me share the screen so that you can see the solution better. Okay. Okay, you see now both of them, right? Can you see both of them?
Yes.
Okay. So basically, if you want to solve this problem here, we have a current passing through a coil having an inductance of 0.5 Henry. So basically, we have, first example, we have L is equal to 0.5 Henry. Henry is the SI unit for the inductance, basically. And we have the current basically changing from 5 to 2 in a time delta t was equal to 0.05 seconds. So basically, if you want to measure di by dt, it's going to be what? 5 minus 2 over 0.05, which is equal to what? 5 minus 2 is 3. 0.05 is basically 1 over 0.05 is 20. So it's going to be 60 ampere per second. Okay. And basically, what he's asking for here is the mean value of the electromotive force. So basically, from this equation right here, it's going to be what? The voltage will be L di by dt, which is equal to 0.5 times 60 equals to 30 volts. You have any questions? Okay. If you want to know exactly how to compute the actual inductance, how to know the value of the inductance itself, or basically compute the inductance as a function of the geometric characteristics of the coil that is making up the conductor, the inductance, basically it has a definition of L is equal to 4 pi times 10 to the minus 7, which is basically what we call omega naught, okay, mu naught, okay, times A, the area of the coil, n square, which is basically the number of turns squared, over L, the length of the coil. A is basically, if you always consider the coil as uniformly wound on a non-magnetic ring, basically, in this case, okay? So basically, let me show you how it should be. Basically, you're assuming that your inductance is basically, you have a certain former, you have a certain cylinder, okay, like this, okay? This is what we call former, okay? And basically, we come with the coil itself and basically wind it over this former, okay? Like this, okay? So basically, this area here is the area that we have in this equation. And you have the number of turns here is at the end of the equation. And the length of this wire is L. Okay? 4 pi times 10 to the minus 7 is basically what we call mu naught. And mu r, if you have if this former is not, if it has some magnetic characteristics, like it's ferromagnetic, if it's made up of iron, basically, if you have a ferromagnetic material like it has iron or can be magnetized, basically we add omega r here. It's mu r, okay, mu r. And basically this mu r is really nonlinear. So basically mu r depends on the material and depends on the current. Okay, so basically it has a very, very nonlinear characteristic. So basically for mu r, assume that you're going to be given the mu r that corresponds to the kind of current you expect it to flow in your inductance. Okay. So basically, whenever you try to compute the inductance, you have to have all these geometric characteristics, and you have to have mu r. If you don't have them, basically it's going to be difficult for you to estimate exactly how much the inductance will be. Mu r, if you have a stainless steel core, for example, mu r can be maybe tens of thousands, maybe up to 100,000, if you can imagine that. Meaning that if you look at this equation, the inductance with a ferromagnetic core can be much higher than the same exact coil that was formed on air, or on plastic, or anything like, for example, wood or something like that is not basically made up of ferromagnetic core. Okay, so if you have air core, is going to be much less than if you have a magnetic core or ferromagnetic core. Okay, let's take an example here. Basically, in this example, I'm going to give you how much omega r will be, but actually there are actual like curves and tables that you can use to do that. But actually, it's really difficult. So I'm going to spare you the effort of looking into things like that. And basically, they are not very useful actually in practice even. Okay. Any question? You have any question? So the first example here, a ring of mild steel stampings have a mean circumference of 400 millimeters. The circumference is 400 millimeters, okay? And the cross-sectional area is 500 millimeters square with 200 turns. Circumference is what? If you look at the coil, basically the coil will be like what we just drew. It's gonna be like this, okay? It's gonna be like you have turns over this, okay? Basically, if you look at it from the side, it's going to look like this, okay? So basically, the circumference is the length here. So the length per turn is the circumference. Okay? So basically, if I want to compute the L, it's going to be the circumference, which is 400 millimeters, times the number of turns, which is what? 200. This is L. This is in meters. And you have the cross-sectional area, 500 millimeters squared, going to be equal to 500 times what? 10 to the minus what? Millimeters squared. We need 10 to the minus 6. Okay? And basically, assume here mu r is equal to 1,000. Actually 10,000, okay? So basically, if you substitute in the equation, you're gonna find out that basically mu naught, of course, is equal to 4 pi 10 to the power 7. So this is what you saw here, okay? And basically, we use this equation. So L will be equal to 4 pi 10 to the minus 7 times 10,000 mu r times the area times n square over L, which is going to be like 400. I just compute that. The second example actually asks you to assume that you don't have a ferromagnetic core here. Assume you have air core. This is ferromagnetic in the first example. You assume that you have air core. When you have air core, basically the part where you have the
Doctor,
the part where you have, yes,
how we get UR from?
You have to be given UR in the example itself, okay, or in the problem itself, because it's very nonlinear, okay. You need to know how much current you will have in order for you to estimate UR. There is a curve in the previous chapter that talks about basically this kind of things, and basically you have to estimate the current. You have to estimate UR based on the kind of current that you will be passing through the coil, okay. The kind of current you have will determine how much B will be, because basically this will generate basically magnetic field like the one we saw in the moving coil. And basically mu R changes with B. So depending on how much B you have, how much magnetic field you will generate, mu R will depend on that, okay? So basically, you get it from a curve like that. But actually, for any problem you will see in this course, I will give you mu r. So basically, I just gave you here mu r.
Okay, thank you.
Okay, assume that you will be given mu r.
Okay, thank you.
So basically, here in the second part, you just assume that mu r here is just equal to 1. Okay, for the second part. The second part in this problem actually is just basically it's exactly the same one. Okay. and basically assume that it's wound on a non-magnetic core. Non-magnetic core can be something like wood, something like plastic, something like air, anything that doesn't have ferromagnetic material inside. Ferromagnetic material meaning that basically iron made material that can be magnetized. Okay, it has a big advantage because it actually makes the inductance much larger, but the problem is that it makes the inductance highly nonlinear. It changes with current. The inductance itself will change with current. Okay? This is the nonlinear part of the inductance. Okay. We're gonna also study the growth and decay in inductive circuits. Basically, each inductance, by definition, because actually it's made up of basically simple electrical wire, like basically like silk addy, like usual wire that you would use to make a resistance. So basically, each inductance, by definition, has also a resistance. Okay, so basically, you will be considering that in each one of the problems that we were going to be talking about. The main advantage or the main characteristic of the inductance is that it doesn't change its current instantaneously. Like exactly for capacitors, it does not, the capacitors do not change their voltage instantaneously. So basically, in the equation that we saw just a few minutes ago, this equation here, the voltage can change instantaneously, but the current has to basically change very slowly. Okay, you cannot change the current abruptly. So basically, for circuits like this, if we have like a battery here, I will connect to this switch at time t equals to 0. We have here the inductance in series with the resistance. What's going to happen that at t equals to 0, the current has to be 0. But the voltage on the inductance will actually create a di by dt that will actually stimulate the current to increase. So basically, we're going to actually do the same kind of analysis that we did before in the capacitors, where we actually compute the growth and decay curves for circuits that have inductances. Okay, so basically, let's do that. So, for example, the first circuit here, the first circuit that we're going to talk about, this circuit here, if we basically assume that at t equals to 0, basically the switch became closed. And basically the current in the inductance initially was 0. Okay, so let's compute the current, how the current will change. It's again, I of t will be equal to I initial minus I final times e to the minus t over tau, okay, plus I final, okay. In this case, as we knew from the circuit course, tau here is equal to what?
L over R.
What?
L over R.
L over R.
Right, okay. So basically, it's going to be like this. For example, for this particular circuit, we have I of 0 here. I of 0 here is equal to what? 0. I of infinity. How much I of infinity going to be? If we have a voltage, the voltage here, assume that it's V. Okay, the voltage here on this battery is going to be V. Okay, at infinity, what's going to happen?
V over R.
Yes. It's going to be V over R, right? Okay. So I at infinity will be V over R. Okay. Because basically, whenever the current increases, it's going to increase to the limit where actually the current here will be V over R. When the current is V over R, this means that this particular voltage will be just a voltage drop on the resistance. The voltage across the inductance itself will be 0. Okay, in this case. So when that happens, when the voltage across the inductance is 0, this means that 0 is equal to L di by dt, which means what? Di by dt will be 0, meaning that it's not going to change. It's not going to increase or decrease. So basically, it's going to remain the same. So I will be constant. Okay. So in this case, the equation here will be what? Will be basically I of t will be equal to V over R 1 minus e to the minus t R over L. So it's going to be exponential growth. It's going to be a curve that looks like this. If we assume that if we have a circuit that looks like this, and basically we shorted the inductance, made a short circuit over the inductance like this. So the circuit in this case will look like this. You will have an inductance and a resistance, and that's it. And you have an initial current here. Assume that we have exactly the same initial current that we had before. The current here at 0 was equal to V over R, okay? And this is R. What's going to happen next? Okay, we're going to apply the same equation. I of t will be equal to I of 0 minus I at infinity e to the minus t over tau plus I at infinity. So this will be equal to I at 0 will be equal to what? It's already there. Okay, so this is basically V over R. I at infinity will be what? How much current passing through the inductance at infinity?
Zero.
Energy in the circuit is coming from the current passing through the inductance. As we're going to see, just like the capacitance. So basically, as we go along, basically, when we pass the current here, this current will pass through the resistance. And the resistance, basically, if you have this particular current here, the voltage across the resistance here will be what? Will be V, right? But if you look at the voltage, it's actually applied in the negative direction on the inductance itself. So basically, we're going to have minus V equals to L di by dt, meaning that the di by dt will be negative and the current will be going down. At infinity, what's going to happen is that basically the current, the voltage here will become smaller because the current here will get smaller, and eventually this will be 0, meaning that the current will be 0 and basically stay 0 forever. So basically the equation here will be I of t equals to V over R e to the minus t R over L. So basically going to be exponential decay. So basically the equations or the growth and decay curves in inductive circuits are very similar to those of capacitive circuits, but the main difference is that the inductance has to be with the resistance. It does not exist by itself because it's basically just a wire wound for many turns, and definitely it will have a resistance because of that. The resistance we saw before was just made of a coil that looks like this. So basically, it must have a resistance. So even if you put a resistance, if you don't put a resistance outside, it already has a resistance inside of it. Let's take examples. A coil having a resistance of 4 ohm. See here, the coil is having a resistance of 4 ohm plus an inductance of 2 Henry. It's the same coil. Okay, it's not like you have a coil and in series with a resistance. No, it's the same coil having both. And it's switched across a 20 volt DC supply, derive the curve representing the graph of the current. This is very similar to the problem we just solved. We have a 20 volt DC power supply, and you have your inductance and your resistance in series. Okay, so basically the initial current will be what? I of 0 will be 0 because the inductance cannot switch from 0 current to any current instantaneously. So basically it has to basically grow the current gradually. And I of infinity will be V over R, which is 20 over, this is 4 ohms, and this is 2 Henry. It's going to be 20 over 4, which is going to be 5 amperes. And the time constant tau will be equal to L over R, which is what? L over R is going to be 0.5 seconds. So basically the curve here will be I of t equal to I of 0 minus I of infinity. I of infinity is this. So basically it's going to be V over R, 1 minus e to the minus t over tau, which is basically 5, 1 minus e to the minus t over 0.5. Okay?
Okay.
You can definitely be asked here, like what we did in the capacitance. For example, the current at t equals to 1 second, for example. Okay? Or you can be asked the time when the current becomes, for example, 1 ampere. In this case, you're just gonna make this equal to 1 amperes and compute T.
Len.
Okay?
Len.
The what? You have a question?
No, Doctor.
Okay. Okay, for the second problem here, you have a coil with a resistance of 4 ohms, and it's exactly the same parameters for this one here, and it's exactly very much the same, actually, same problem, but you need here to compute the time constant. Time constant, we already did that. The final value of the current, we already did that. The value of the current 1 second after switch is closed, okay? So meaning that I'm just gonna have to substitute here T equals to 1. So basically just put here T as 1 and see what this value is. These kinds of problems, actually, you should have had that in other circuits courses. These are very simple problems, actually. Do you have any questions about this kind of problems? Okay. Another circuit here, this is a kind of circuit where you have switching in the middle. So here you have 0.1 Henry in series with 10 ohms resistance. Basically, the coil itself has a 10 ohm resistance. And basically, at t equals to 0, this came here to position 1. Okay? So basically, when it's at position 1, you want to determine the mathematical expression for the variation of the current in the inductor following the closure of the switch at t equals to 0. So basically, we're talking about this part of the circuit now. We have a circuit that looks like this now. It's exactly the same problem that we saw before, and the solution is going to be exactly the same. So basically, you can do it right away. I of t will be equal to, let's just compute tau first. Tau will be equal to L over R, which is going to be 0.1 over 10 is going to be 0.01 seconds. I over t, what I of t will be final current. Final current will be basically 10 over 10. V over R, V over R, which is going to be 10 over 10, which is equal to 1. So it's going to be 1 minus e to the minus t over 0.01. Okay? So the first part here is done like this. When the switch is closed onto position 2, at t equals to 100 milliseconds. So basically, I need to compute I at 100 times 10 to the minus 3 seconds. Which is going to be equal to what? Basic substitute here, this is equal to 0.1 basically, okay? 100 milliseconds, okay? So basically it's going to be 1 minus e to the minus 100 milliseconds 0.1 over 0.01 is going to be 10 to the minus 10. This is almost 0, by the way. So basically this is approximately 1. So now, when it's in position 0, okay, which is in position 2 after 100 milliseconds, what's going to happen is that the inductance will have to continue to basically pass the current along the circuit here. Now you have an additional resistance. So basically after 100 milliseconds, the new tau dash will be equal to what? L over R dash, which is 0.1 over 10 plus 25, 10 plus 50. It's going to be what? 0.004 seconds, right? Is that correct? This is 1 over 4 over 100, okay? If you take 100 here, you have 2 zeros and multiply by 4. This is going to be like this. And now, for this particular circuit, what's going to happen is that I of 0 is equal to the current here, which is going to be 1. Okay? And basically, I of infinity is going to be what? 0. So the current, the equation of the current will be I of t after 100 milliseconds will be equal to 1 times e to the minus t over 0.004 seconds. Okay? And basically this will be like an exponential decay. This will be like an exponential growth to 100 milliseconds. And from there, you actually have to go down. You have nowhere but to go down, basically. Okay. But you're gonna go down much faster because the time constant is much smaller. Okay. You have any questions about this kind of problems?
It's clear.
No, clear.
Okay.
Doctor, do we have to draw the graph in the exam?
Just draw it. You don't have to draw it to scale, but at least you have to show me that it's going like exponential growth or exponential decay, things of that sort. But that's it. You don't have to actually make it to scale or anything like that. Usually, what I would ask you to do is just get the expression. Okay? From the expression, it's clear, actually. It's clear if it's going to be this or that. So
okay.
in the exam that you'll see only the, you basically have to write only the expression. You don't have to draw it. Here he's asking you to do that just to make sure that you understand how this will look like. If you have an equation like this, you just want to make sure that you understand that this will be basically exponential decay. If you have an expression that looks like this, he needs to understand that you know that this is an equation for basically exponential growth, and that's it. Okay, so the energy stored will be basically very similar. It has a similar formula to what you saw in the capacitance, but for the capacitance, what you're storing is charge, and this charge will cause the voltage to be there. And basically, this is why it has an energy equation that was 1/2 CV squared. Okay, here what you have is 1/2 Li squared. Okay, can we prove that? Is it possible to prove that like we did last time? Actually, we can. If you go back here, you have basically V is equal to L di by dt. And basically the power is equal to V over I times I. And the energy is the integration of V dt. Compute VI, this will be equal to L di by dt or Li di by dt. Okay, you integrate that with respect to t. L will go outside. So basically, I di by dt will integrate to I square over 2, right? And you have L here. So basically, the energy stored will be equal to L I square over 2. Of course, what we said before about having a ferromagnetic core, the energy does not change uniformly like this with the current, because basically the inductance will change with the current. So when you have a ferromagnetic material, I need to emphasize this again, what you're going to have here is that this L here will be a function of current. So basically, when you have a current that changes like this, okay, that changes with time, you basically, you have L that is dependent on the current here. So basic things are not going to be as nice as it looks like there, right there, okay? Because what you're going to have here, basically, this dt goes with this dt. So basically, if you have L as a function of I, then it has to go into this integration. So this will not come out like this if you have L that depends on the current. So basically, the equation when you have the energy as 1/2 Li squared is a simplified version of the actual thing that happened in reality. So basically, what you do usually is you compute the current that is basically the most common current that you're using, or the baseline current, and you compute the L at this baseline current and assume that it will be constant around it, and basically assume that the 1/2 Li squared will be valid. But this is actually just an approximation. Just make sure to understand that this is not a simple or a linear or as basic as it was in the capacitance. If you have an air core, then you don't have any problems. You can just use this equation without any difficulty. It's going to be exactly the same. Okay. Now we need to talk about the mutual inductance, which is basically the last part here in this part about the inductance. I'm not sure actually if you heard about the mutual inductance before or not. Have you heard about it in the circuits, in the 250 or 301 courses?
Basic 250.
250.
So
basically, basically this whole part I think is probably exactly the same as the one you saw before. So basically the idea about the mutual inductance is that if you have two coils like this, and they are basically connected to each other through the same magnetic circuit meaning that if you have the same core, okay, or basically if the flux from one of them affects the other, then what's going to happen is that the total value for both of them will change depending on the interaction between them, okay? About the basically the interrelationship between the two inductances, which is what is called the mutual inductance. So basically, if you have a current passing through this coil, for example, the current, the voltage, there will be a voltage induced in the other one that is equal to M12, which is the mutual inductance between coil 1 and coil 2 times the I by dt. So basically, for this coil, you will have LdI by dt, okay, for the voltage. But you have also another voltage here induced by the magnetic field flux generated by this one, which will be equal to this. And basically, instead of having the inductance of this one here, we have the mutual inductance. The energy is the most important. The energy, if you have two coils like this connected, either basically connected if you're passing the current in the same direction, meaning that they are going to both induce flux, magnetic flux in the same direction. So for example, if you're passing the current, both of them are actually passing the current this way, this here and this here, okay? So these are basically, these will enforce each other, because basically they are trying to, basically their magnetic fields will interact constructively. If you're passing the current in the opposite direction, for example here, what's going to happen is that the energy stored will be a little bit less. So basically the energy will be equal to the energy computed from the basic equation that we saw before, and the basic equation that we saw before for the second one. So this is for the coil A, and this is for the coil B. And then you will have another component that depends on the mutual inductance between the two coils. And base can be positive if you are constructively interfering, or negative if they are destructively interfering, okay? So basically, it's going to be plus M12 IA IB if they are in the same direction, or minus M12 IA IB if they are in opposite directions. So here the mutual inductance, basically we just say it M, okay? If you have two coils, just consider that it's M, okay? Because M12 is equal to M21. So the effect from coil 1 on coil 2 will be exactly the same as the effect of coil 2 on coil 1. And basically, the coupling, you can actually relate the M to the actual inductances in this equation right there, which is basically in terms of something called the coupling. Okay, the coupling coefficient. Okay, so basically M will be equal to K square root of L1, L2. Square root of L1, L2, by the way, is the geometric mean of the inductances. Of course, we know the algebraic mean. Algebraic mean is the average, basically. Average is basically L1 plus L2 over 2, right? But just taking the average of two numbers, okay? If you multiply the two numbers and take the square root, this is called the geometric mean, okay? So basically, the M is the geometric mean of the two inductances multiplied by K, and K is called the coupling coefficient. If basically the coils are close together, then K will be large. If they are apart, far apart, and basically are loosely coupled, then K will be very small, okay? So for example here, basically, they put a dot here in the direction of the current. So basically, they know to know the direction of the coil itself. So basically, the inductance of the two in series will be equal to LA, LB plus twice M. If they are connected in opposite directions, so basically the current here is passing in this way from this terminal to this terminal, and basically it's passing on the opposite direction here. So basically the magnetic field flux from one coil will be opposite to the other from the other coil. In this case, the inductance will be, the total inductance of the summation will be LA plus LB minus twice M. Okay, in this case, if you connect them in this case like this, M will be equal to L1 minus L2 over 4. So basically, we can have several examples of how to solve problems like this. When you have two coils connected in series, their effective inductance was 10. When the connection to one coil is reversed, basically the effective inductance became 6. If the coefficient of coupling is 0.6, calculate the self-inductance of each coil and the mutual inductance. So basically you have a situation like this. You have this is equal to 10, and this is equal to what? This is equal to 6, okay? Let's try to solve it. Basically, what you have here for the first one, the first piece of information was that 10 is equal to LA plus LB plus twice M. Okay, and 6 is equal to LA plus LB minus twice M. Okay, and basically you have another equation or another given that K was equal to what? K was equal to
0.6.
0.6. Sorry, 0.6. How many equations and how many unknowns we have here? How many unknowns? We have LA, LB, and M. Right?
3.
How many equations?
2.
We have 2 equations. Actually, there's another equation where we saw that M was equal to K square root of LA, LB, right?
Yes.
Let me go back. Okay. Here we're talking about 2 coils, L1 and L2. Okay. It's basically the same here. We have coil, the first one was LA, the second one was LB. So basically here we have a third equation, and this third equation is actually in terms of this. So basically you can substitute this here. Actually the easiest thing is maybe just if you add these 2 equations together, the first 2 equations here, just add these two together, what's going to happen? Or subtract them, I'm sorry. If you subtract these equations, it's going to be 4 equals to 4m, right? You can get m, okay? And from m, you can actually, through this equation, you can have LA as a function of LB. It's going to be what? Just square this equation. Here here m will be equal to 1, k is equal to 0.6, okay? So if you square this equation, this will be like LA LB times 0.36 is equal to 1. So you can actually get LA as a function of LB from this equation and basically substitute it here to get the other one. Okay, so you just have basically in this case, once you get m, you have two equations and two unknowns. So that just basically solve them to get LA and LB. So basically here, what you need to do is just compute the self-inductance LA and LB. This is what was required, basically. Okay. Once you do that, you can actually compute the mutual inductance as well. The mutual inductance, you already computed that from just basically subtracting these two equations. So basically, you already got the, I'm sorry, here actually, no, that's right, that's correct. Once you subtracted these two equations, you already got M, the mutual inductance. And once you got the mutual inductance, you got another equation in terms of that has only LA and LB. And you already know how much is this and how much is that. You can just substitute its value from here. So you have two equations. Basically these two equations will be exactly the same because you already used them to get the M. So just use one of these equations, basically this one here and this one here, to compute LA and LB. Okay. Okay. There are several types of inductors, as we said before, but actually let's talk about the general types. Basically, we have the air core inductance, and we have the ferrite or ferromagnetic core inductance, and basically you have the variable inductance. Okay, the air core, we already talked about it. Basically, you have a formula that is not ferromagnetic, like air, like wood, like anything like that is not ferromagnetic. It's not made up of iron. For the ferromagnetic core, you basically have a piece of iron in the middle here, and basically you wind your wire around it. And basically it can be much higher, but actually it changes with current. It can be much higher in value, but it's not a linear inductance. Basically, it's not going to be like a fixed inductance. If you change the current dramatically, you expect the inductance to change accordingly. For the variable inductance, actually, it's much simpler than what we saw before. This looks like, basically, let me draw it for you. Basically, if you have a coil like this, okay? If I have a ferromagnetic core basically is something that looks like this. Okay, the ferromagnetic core can actually, let's just draw it inside. Okay. For some reason, it's not responding. That's fine. Basically, you have your ferromagnetic core here. Okay. If you move it, what's going to happen is that part of the coil. Let me draw two situations. If you look at this coil actually from the side. Okay. If this core was like this, then basically you have all the windings or the turns here around that ferromagnetic core. If you actually move it a little bit outside, it's going to look like this. Basically, you're going to start from somewhere here. And basically, if you have some windings here, there will be air core. So basically, when you move it outside, what you're doing is basically changing the inductance by basically making a part of the coil as air core rather than ferromagnetic core. So if you move it even the slightest movement, this will affect the inductance to a great extent. You see these parts actually, if you look at a radio, if you have an old transistor radio from a long time ago, basically you see components that looks like this, like a very small box on the printed circuit board, and basically by changing the position of this screw with a screwdriver, you actually, what you're doing is doing something like this. This screwdriver determines the position of this ferromagnetic core inside the coil. And this actually can be used to do some kind of tuning of this inductance. So basically you change the inductance to make it in tune with a particular frequency, for example. Okay, if you want to have a certain frequency or if you want to have a certain inductance, you basically change this position, change this screw. When you change the screw, it's just like any screw basically. What you're doing is you're basically taking this screw which has which is connected to the ferromagnetic core. You change the position of it inside the coil. When you do that, you're changing the inductance because a part of the coil became basically air core. The more of the coil becoming air core, the smaller the inductance. If you have the core all the way, you know, across all the windings or across all the turns, then you got the maximum inductance. Okay, so basically you change the inductance this way, and this is the only way to create a variable inductance, by the way. Okay, it's not as easy to create an electronic variable conductance like variable inductance like what we saw in the capacitance. In the capacitance, we used a diode, and basically there was a technology actually that uses something that uses the reverse polarity of the diode, the depletion zone. When you have a reverse voltage, you basically use that to create variable capacitance. Here you cannot, which is one of the parts actually. One of the things that you have to worry about in the inductances. If you have an inductance inside an electronic circuit, you cannot change it electronically. You have to change it basically using a mechanical means. That's why when you have a resonance circuit by definition has an inductance and a capacitance. You choose to change the capacitance electronically because actually you cannot change the inductance electronically. Okay? Any questions? So basically, one of the parts that you have to one of the parts that you have to worry about is basically the insulation. Okay, the problem with the insulation is that you have a coil, and the coil you have like the transformer basically. The coil will have a wire that is insulated, and basically if you pass a large current in that coil, there will be enough heat in the resistance of the coil to basically melt the insulation. When this happens, this will short out a few turns together. When you do that, basically it changes everything. It basically becomes a short circuit at the end. Okay, and this can be a problem. Okay, so you worry about passing a large current in this kind of components because actually it can short circuit and create a problem in your circuit. Okay, so basically probably next time I'm going to show you a picture of how it looks like, how it actually looks like, and basically when you see that, you will know that it's very common for something like this to happen actually. Okay. So let me try to get a picture like that for you. Just a second. I think I have a picture. I don't see it now, but I'm going to find one for you. Don't worry about it. I thought I have one, but actually I don't have it. Okay, I don't have it now, but it's fine. I'm gonna give you a picture of that in the resources. I'm gonna post it on the Blackboard, and basically next time I'm gonna show it to you. The last thing in this lecture is actually about the ideal transformer. Basically, we're not going to talk much about the ideal transformer. Basically, it's just an ideal transformer. It's just going to be like the ratio of the voltages is exactly the same as the ratio of the number of turns. And it's opposite for the current. So basically, if you have V1 over V2 approximately equal to N2 over N1, it's going to be opposite like I1 over I2. Basically, it's because the power in the input circuit here should be exactly the power in the output circuit. And of course, you have to know that basically this actually works by transferring the energy from one coil to the other through the magnetic core. You have to have a magnetic core here. And basically, due to the fact that the magnetic core is usually lossy, it has some ways to lose the power, you cannot have exactly V2 over V1 equals to N2 over N1. You lose some energy or some power in the middle in this conversion. Okay? So basically, this can be a problem. But let's just get into the definition of the different parts in the transformer. Basically, this kind of transformer is called isolation transformer. Isolation transformer meaning that you have a different coil for the input circuit than the output circuit. They are not connected together. This is opposite or different from something that looks like this. If you're talking about what we call auto transformer, the auto transformer is just like a core, okay? And basically you have, this is the input. And basically the same coil actually continues, the same coil, and basically the output can be basically from another terminals here, but they are actually connected together. So basically it's the same coil. Okay, and basically you take different turns or different taps from this coil and basically create the input and output. So basically they are connected together. They are not isolated. Isolated meaning that you have one here and one there. They are not connected together. You have separation between the two. You don't have connection between the two. For the auto transformer, it looks like this. Auto transformers are actually used in situations where you don't worry about the isolation that much. Remember that we used an isolation transformer when we wanted to have a different ground, for example, for the oscilloscope, okay? But actually, not so many people worry about that. For example, your computer, if you have a desktop computer, the switch mode power supply that it has, it uses an auto transformer, not an isolation transformer, because actually it's much smaller, and basically you're not really worried that much about the isolation. So basically, if you look at the different parts of the transformer, you have basically the vertical parts here are called limbs. Limbs like atraf, okay, limbs, okay. The top and bottom portions are the yokes, okay. This here and this here are the yokes, okay. And basically, you have the coils. The input coil and the output coil are wound on the limbs, okay? And basically, the part that is connected to the supply, the input, is called the primary coil, or the primary part of the transformer, basically, okay? The other coil that's connected to the load is called the secondary coil, okay? So basically, this is the secondary coil and this is the primary coil, okay? And basically, this is the load where you have your power source here, you're supplying the load here a different voltage. This is used in so many applications. I can give you many applications about transformers. We use this, for example, in electrosurgical units. where you have a very small voltage, you generate a very small voltage with very high frequency, and you basically use a transformer that, like this to raise the voltage to thousands of volts. Okay, so you can do that with a transformer. Okay, this relationship, as I told you, is approximate because basically you have some losses. The basic equation is that the power input is equal to the power output. Okay, and the power input is basically V times I here, and this is V times I here. That's why you have these two are opposites basically, because basically V2 over V1 is equal to I1 over I2, because V2 times I2 is equal to I1 times V1 approximately. The power input is equal to the power output. Here you have a very simple example. You have a 250 kilovolt ampere, 11,000 volts, 11,000 volt to 400 volts transformer. This is 50 hertz. It has 80 turns, and the secondary on the secondary, calculate the approximate value of the primary and secondary currents. First of all, here you have it's 11,000 to 400. The ratio between the primary and secondary currents will be opposite to that. Okay, and basically, if you know exactly how much, if you know how much power you have in the input, you can actually use that because you have the input here as 11,000 volts. You can actually, given that, you can divide this, the power, over the voltage to get the current in the primary. And when you have the ratio of the primary to secondary voltage, this is exactly the same in opposite to the current for a primary over the current at the secondary. So basically, if you have, let me just write the equations, just simplify it. Here, basically, can you see both the slides and the note?
Yes, yes.
So basically, you have 200 kilovolt ampere is equal to 11,000 times I, the I1. Okay, this is V1. So basically, you can get I1. And you have 11,000 over 400 is equal to N2 over N1, which is equal to I1, I2 over I1, the opposite. Okay, you have that, you can compute that. Okay, so here you computed I1, here you computed I2 from this equation, and the third one, the other requirement is you need the primary, the number of primary turns. You need here N1, how much N1 is. Okay, if you have 80 turns here, you're given that, this is like 80, you can basically compute that from this ratio right there. So you can get that as well. So basically, these kinds of problems are really very simple, actually. They are not that evolved. I'm sure that you had a very similar problem to that in probably 250, right? You had transformers in 250, right?
Yes, doctor.
Yes, please.
Exactly the same. Okay, the final part is related to the losses, the practical transformer issues. First of all, if you see how the relationship between the voltage and the current, and basically if you have the magnetic field and the magnetic field density, if you look at how the magnetic field changes in the core, you will find that when you're raising the current, it goes in one direction, or goes in one curve, and basically it's going back, it goes through another curve. So basically, whenever you have a hysteresis like this is called a hysteresis. Whenever you have a hysteresis like this, the area in the middle represents losses. And basically, these losses are related to the energy that is required to basically magnetize the core and demagnetize the core. Imagine that you have an AC waveform that has 50 hertz or 60 hertz. Whenever you have a positive voltage, then you're charging or basically magnetizing your core in a particular direction. You have the north and south poles of the ferromagnetic core in particular directions. Whenever you have a negative voltage, you have the opposite of that. So basically, the magnetic core will basically change the polarity of its magnetic field. So the energy required to magnetize the core in each cycle, basically to make it positive and then make it negative. It's not for free. These things happen with, it requires energy to happen, actually. They require energy to happen. So basically, there are some thing called hysteresis losses, which make the whatever component that you use with ferromagnetic cores basically lossy. Because basically, if you have a transformer, for example, you will find that the energy output is not exactly as the energy input. You take more energy, you put more energy input to get the same energy output, basically. Okay, because of the losses through the hysteresis. Basically, we're going up and down, magnetizing and demagnetizing your ferromagnetic core. You basically lose energy in that each cycle. There's another source of losses that is related to what's called the eddy currents. You have basically, whenever you have a varying flux in a core, this induces EMF. Whenever you have a conductor, any conductor, not just a ferromagnetic core, basically. If you have a core that is made up of copper, for example, okay? If you have varying magnetic field, it's going to generate EMF in the core itself. And whenever that happens, it will pass current through the core, and this current will have an I squared R losses. You will have basically heat losses through the resistance of the ferromagnetic core, or the magnetic core, or the conductive core in general, okay? So basically, this actually loses energy from the transformer or from the coil or whatever through heat. So after a while, if you have a transformer and you let it work for a while, you will find that this transformer will actually heat up, okay? And this heat actually is a source of loss. So you're losing energy through that heating of the core of the coil or the transformer, okay? If you combine these two, if you have ferromagnetic core, it will have both components, and in this case, you will call both of them as core losses, okay? Core losses involves hysteresis losses required to basically generate the magnetic field and change it with each cycle. And the eddy currents in losing energy through the heating of the core that is resistive, basically. Basically, if you have a magnetic or basically if you have a metal core in general, you will have eddy current losses, and basically you will lose some part of your energy into heating. And basically this will basically make both of them as core losses. Basically this is it for the inductance. I'm not going to talk more about it. I'm probably going to basically ask you very simple questions about it in the exam. The main applications of inductors are basically twofold. You use them in filters and you use them in power supplies, okay? Mainly, okay? Power supplies, if you talk about, for example, like if you have a certain voltage, 5 volts, and you want to convert it to 12 volts. There are switch mode power supplies that use inductance to do that. You will need an inductance to be able to do that. For the filters, this actually has been the trend for a while, but actually now they are trying to cut down on the use of inductors in filters. So basically, most inductors right now are used in power supplies, not in filters. For the transformers, of course, we have so many applications for transformers. Okay, like the application I just told you about the generation of very high voltages. You can actually think about so many applications, actually, like X-ray imaging, for example. You generate 100 kilovolts or 125 kilovolts, okay, from regular AC mains, okay? So basically, you have to have a transformer to allow you to go up to that much energy, how much voltage in the output. So basically, the transformers are actually widely used. But the inductors are mainly used right now in the design of power supplies. Okay, you will have some questions related to that in the project, but actually I'm not going to ask you about applications of inductors in the exam or anything like that. Okay, you have any questions? Okay, let me just emphasize again the things that I asked you about at the beginning of the lecture. This will be it. please submit your lab reports, okay, as soon as possible. Okay, the previous lab reports, not just the new ones. Okay, so basically, for lab 6 and 7, you will have to simulate and submit the reports based on the simulation, just the simulation. You will have about 10 days to do that for lab 6 and 7. For lab 1 and 5, I'm asking you to submit this weekend. You should already have these reports. Please submit them because Engineer Mutahar doesn't have your reports. The hard copies that he received from you are in his office. We have no access to them. I'm not sure we ever have access to them before the end of this term. We have to post your grades in about maybe two weeks, something like that, not more than that. So basically, we need the reports. We need you to submit the reports again so that Engineer Mutahar will grade them again and post your grades so that you can ask him if you have any complaints, or if you see that your grade is below that what you expect, you can contact him before the end of the term. For the lab exam, I'm going to agree with you how the lab exam will be like. I'm going to probably send you exactly how the question will be like. And basically, we will determine that after you submit experiment 6 and 7, because basically they will be included. For the projects, please submit your team members to me. So far, I received only 2 teams. And please try to have as many as 4 or 5 students. One of the teams I received actually was 3 students. This will make the effort a little bit larger for each one of them. I'm not going to basically say that this project, this report doesn't have everything, but they have only 3 students, so it's fine. No, you have to actually fulfill all the questions. Basically, I'm going to grade the report without knowing actually how many students contributed to that report. After that, I'm going to give the same grade to all of them. So if you have 4 students, you have an advantage. If you have 5 students, you have even more advantage. So don't worry about having a lower grade if you have less students or more students, okay? So please submit your group, your project teams to me as soon as possible so that I know that you started already, okay? You have any questions?
دكتور معلش، هذه المحاضرة مسجلة ولا؟
أيوة نعم. في حاجة؟
معلش لأنه لا دوبي دخلت بس.
لا مش
ناسي إنه في محاضرة.
لا البوست دلوقتي حالا ما تقلقش.
تمام الله يعطيك العافية.
بص أنا أول حاجة مش عايزكم تقلقوا من أي حاجة على فكرة، يعني أنتوا بالنسبة أنا قلت لكم إن الميد تيرم إكزام الجريدز هتتعدل، بس أنا تعودت إن أنا أعدل في الآخر خالص. يعني في آخر الترم خالص قبل الفاينل هعدل كل درجات أو basically modify all the grades based on basically the sum of all the parts of the evaluation, the homeworks, the lab, and everything, the midterm, and basically I'll basically add more marks to each one, basically each student, and basically make sure that the curve is actually around basically B. Basically, the average should be B. Okay. So basically, I'm going to wait to do that right before the final exam, if there is a final exam. So far, we don't know if we have a final exam or not, but at least for the grades, for the course grade, don't worry about them. Just try to submit all the assessment tools, all the assignments, all the reports, do the project, everything. And basically, if you do that, don't worry about anything. I'm sure you will get a good grade. Okay. Inshallah, next week, we're going to start with the sensors. And hopefully we'll basically finish the sensors next week. So we'll have additional time if you want me to go back and basically explain anything else. But actually, as far as this course is concerned, the material of the course will finish by the end of next week. Okay? Because actually I don't want to push you much further than that because I know that you have other classes. I'm not sure exactly how many assignments that you have to turn in by the end of the term. So I just want to give you a cushion, like a week at least of basically without any new material so that you can ask about the old material, you can prepare for the final. If there is a final, you can finish your assignments and basically ask about anything that you need to be basically that needs explanation again or anything like that. Okay? Okay. Please send me any questions you have, and basically I'm gonna continue to post the notes and the recorded lecture on the Blackboard as usual. Okay?
Okay.
And good luck with all. Stay safe, please. Okay? This is the most important thing right now. Stay safe, please. Okay? It's not time for going out or gathering or anything like that, please. This is a very critical time, and basically your safety is much more important than anything else. If you think that any of the assignments, anything related to this course or any other course might require you to jeopardize your safety, please put your safety first, okay? And ask the vice dean, ask your instructor, ask the chairman. They will actually be very responsive to your complaints or any thing that you might be worried about. Okay?
Okay,
Safety first, okay? Good luck, inshallah.